Hi everyone, I am Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about magnetic materials and their important properties like permeability, susceptibility and the relationship between them. So let us see the topics we have covered thus far about dielectric materials. We have seen the introduction and all the terms that are involved with dielectrics. We have seen the types of polarization and we have derived expressions for the internal field in solids and also the Clausius-Mosatti equation, which is a very important equation in dielectrics. And also we have seen about ferroelectricity. So we'll be discussing about magnetic materials. In the introduction part, we will be basically discussing about different terms and their relationship between each other. Now, when it comes to today's topic, we will see how we are going to discuss about it and the brief outline. So first we will see the introduction, what are magnetic materials and what is a magnetic dipole, magnetic flux, intensity of magnetization, magnetic induction, permeability, then relationship between B, the magnetic flux, the magnetic field strength and the magnetization H. And also we are going to see and understand the origin of magnetic moment in magnetic materials. So let us now see the introduction. In the introduction, what we are going to see is what are magnetic materials and how the magnetic effect is seen in magnetic materials. So, the magnetic effects in magnetic materials are mainly due to the magnetic dipoles. So, whatever magnetic effects we see in a magnetic material, they are due to dipoles. So, what are these dipoles? So, these dipoles are a result of the effective current loops in the atomic orbits and also from the effect of electron spin and from the magnetic moments of atomic and atomic nuclei. So whenever we are talking about a structure of an atom, we have the nucleus at the center and electrons revolving around the nucleus in fixed orbits. We have the electrons revolving like this in fixed orbit. So now when we are talking about a magnetic material, the magnetic effect is due to the magnetic dipoles, and how these dipoles are formed, they are a result of the current due to the loop of electrons. So whenever these electrons are revolving round the nucleus, they constitute current, and that also gives rise to dipole. And also we see the electron spin. So the electron, when it is revolving around the nucleus, it is also spinning about its own axis. So that also gives rise to electron spin, which contributes to the magnetic moment. And also from the magnetic moment of atomic nuclei. So in the nucleus, what we have, the protons and neutrons, they also contribute to the magnetic moment. So like that, we see the effects, magnetic effects in magnetic materials. Now all these motions of charged particles, they form closed current loops and they are equivalent to magnetic dipoles. So these closed electric currents are behaving like magnetic dipoles. And now when these dipoles, they are subjected to external electric field. When we are applying an electric field, what happens? They will experience a torque and they will tend to align their magnetic moments in the direction of the applied field. So when you have the magnetic dipoles and when an external field is applied to these magnetic dipoles, they experience a torque. And because of this, they align themselves in the direction of the applied field. Now, when we have to just define what a magnetic dipole is, each tiny dimension of a magnetic material or an atom in a magnetic material, we call it as magnetic dipole. So, each dimension we are talking about, be it an electron revolving around the nucleus or the atoms or the particles inside the nucleus, they all contribute to magnetic moment and they form magnetic dipoles. So these magnetic dipoles are producing the magnetic moment depending on the alignment with the applied magnetic field. Now let us see what is magnetic field. So how do we get a magnetic field? The magnetic field in which a material is kept is called a magnetizing field. So how do we get the field and why it is called a magnetizing field? So whenever we take a material and keep it in a magnetic field, then the magnetism that is produced is due to the magnetic field. So we call it as magnetizing field. And the strength of this magnetic field is denoted by H. So the strength of the magnetic field, we call it as intensity of the magnetic field or simply the magnetic field. It is denoted by H. And what are the units in which we measure this magnetic field is ampere per meter. In the SI system, we are measuring it in terms of ampere per meter. Now, when it comes to a magnetic field, they are produced by permanent magnets such as horseshoe magnet. So whenever we are talking about a magnet, we talk about different kinds of magnets. I say this is a bar magnet. So when I am taking a bar magnet, this is the North Pole and this is the South Pole. So we always have the lines of magnetic lines of force like this. So inside also we have, but in the other direction. So these are the magnets. So when I'm talking about a magnetic field, I have taken a magnet, or you can also take a horseshoe magnet like this. This is what we call it as a horseshoe magnet. One is north and the other is south. So the lines of force that are passed, all this is the field. And the strength of the field, we call it as intensity of the field. So this can be produced due to permanent magnets like a horseshoe magnet or also temporarily by electromagnets. So what are electromagnets? You take a material and as long as the current flows through that material, it behaves like a magnet because the effects of electric current are magnetism here. Next comes the term magnetization. What is magnetization? The magnetic moment per unit volume that is developed inside a solid is called magnetization. Magnetization is what? It is the magnetic moment per unit volume. And it is denoted by M, capital M. Magnetic moment is denoted by small m generally. And the magnetization is denoted by capital M. Then the SI units are ampere per meter. And since this magnetization is induced by the field, whenever we are keeping a material inside a magnetic field, so the magnetism is induced in it. So what we assume is M should be proportional to H. H is the intensity of the magnetic field. So as the strength or the intensity of the magnetic field increases, the magnetization also increases. So we write M is proportional to H and we can write the proportionality constant as chi. And this is called the proportionality constant or susceptibility, magnetic susceptibility. So this is the formula we have for magnetization. M is equal to chi into H. So what is this magnetic susceptibility? How can we define the magnetic susceptibility? So magnetic susceptibility of a material is a measure of the ease with which it can be magnetized. So how easily a material can be magnetized, it depends upon the susceptibility of that material. If the susceptibility is high, it can be easily magnetized. If it is low, it cannot be magnetized easily. So it is defined as the magnetization produced in the material per unit applied magnetic field. So just now we have seen the formula for chi. Chi is equal to m by h. So m here is denoting the magnetization. M is the magnetization and h is the intensity of the magnetic field. Intensity of magnetic field. So chi is equal to m by h. Now materials that have high susceptibility, they can be easily magnetized. We can magnetize them very easily. Then comes the magnetic flux. What is magnetic flux? It is defined as the amount of magnetic lines of force passing perpendicularly through unit area of a given material. So if I have a material that is placed in a magnetic field, what are the number of lines of force that are passing through the material per unit area? That gives us the magnetic flux, and that is denoted by phi. And phi is equal to A into B. What is A here? A is the area of cross section of the material and B is the magnetic induction. So we can measure the magnetic flux knowing the magnetic induction and the area of cross section of the material. And this magnetic flux is measured in Webers. In SI system, we measure it in Webers. Now, this magnetic induction at a point is defined as the force experienced by a unit north pole placed at that point. What is magnetic induction? So, magnetic induction here is defined as the force that is experienced by a unit north pole that is placed at that point and is denoted by B, and B is equal to phi by A. Phi is nothing but the magnetic flux and A is the area of cross section. So the unit for the magnetic induction B is Weber per meter square. Phi, the flux, phi here is the magnetic flux. Phi is the magnetic flux which we are measuring in Webers, Weber. And A is the area. Area or area of cross section we say, which is measured in meter square. So the SI unit will be Weber per meter square. Now when in this magnetic induction, what we see here is the medium is exposed to a magnetic field of intensity H and it causes an induction B in the medium. So B should be proportional to H. Means more the strength of the magnetic field, more the magnetism that is induced. So we write B is equal to mu H, where mu is the permeability of the medium. We call it as absolute permeability or simply permeability of the medium. Now, the magnetizing field strength, if it is air or vacuum, means if the material is not placed in a medium but it is placed in air or vacuum, we write B is equal to mu naught H, because mu naught here is the permittivity or permeability of free space. Mu naught is the permeability of free space or vacuum. So what is the value of mu naught here? It is a constant which is 4 pi into 10 power minus 7 Henry per meter. So whenever we are placing it in a medium, we are writing B is equal to mu H, where mu represents the permeability of the medium, and when we are placing it in free space or air or vacuum, then we write it as mu naught H, and mu naught is a constant 4 pi into 10 to the power of minus 7, and the units here is ampere per meter, same as B. Now, what is this permeability? We are talking about the permeability. So, what is permeability? What is its significance? It is the ability of the medium to pass the magnetic lines of force through it. So when the medium is allowing the lines to pass through them, then you say it is permeability. It is permeable. So if it does not allow, so the permeability is very less. So we have three permeabilities: mu, mu naught and mu r. So what is the relationship between the three here is mu is equal to mu naught into mu r. What is mu? Mu is the absolute permeability of the medium. We have seen just now. We also seen about mu naught. It is for the free space, permeability of free space, air or vacuum. And what is mu r? Mu r is called the relative permeability of the medium. So generally what we define mu r as mu by mu naught. Mu r is the relative permeability, which is the ratio of the permeability of the medium to the permeability in free space. So this ratio gives us the relative permeability. Now we are going to see the relationship between B, H and M. What is B here? B is the magnetic field induction or magnetic induction. And H is the magnetic field or the strength of the magnetic field or the intensity of the magnetic field. And capital M here represents the magnetization. This is magnetization. So what we see here is when a material is kept in a magnetic field, two types of induction arise. There are two types of induction that are taking place. One is due to the magnetizing field H and the other is a consequence of magnetization. Means the material is getting magnetized. So because of that there is a magnetization. So the magnetic induction B that is produced inside the material will be B is equal to mu naught into H plus M. H is the applied or the magnetizing field and M is the magnetization. So the magnetic induction B depends on both H and M. So B is equal to mu naught into H plus M. What is mu naught? We have seen it is the permittivity of free space or vacuum and its value is constant 4 pi into 10 power minus 7 Henry per meter. Now we are going to see the relationship. What we have seen here is B is equal to mu naught into M plus H. So what is M we have seen? We have seen the relation for chi. Chi is equal to M by H. So this implies M is equal to chi H. So I am going to substitute this value. I take this is equation 1 and this is equation 2. I will substitute M value, M from 2 in equation 1. So what do we get? B is equal to mu naught into chi H plus H. So I can take out H outside. So B is equal to mu naught into chi plus 1 into H. Or this chi plus 1 is nothing but mu r. So we can write it as B is equal to mu naught into mu r into H. And we know mu naught into mu r is equal to mu. So we write B is equal to mu H. So what we get here is B is equal to mu H or B is equal to mu naught into mu r into H. So mu is the permeability of the medium. And now whenever we are placing this in free space, when we place a magnetic material in free space, there is no medium. So it should be either air or vacuum. Then what happens to this expression B is equal to mu naught into M plus H. So what happens here is this M becomes 0. M is equal to 0 in free space. So when M becomes 0, what we have simply is B is equal to mu naught into H. So in free space, we write B is equal to mu naught into H. And if there is any medium, we are placing it, we write it as B is equal to mu naught into M plus H. Now coming to the magnetic susceptibility. We have already discussed what is susceptibility. It is the ratio of the magnetization to the magnetic field intensity. So H is the applied magnetizing field, M is the amount of magnetization. So chi is equal to M by H. And chi is equal to 0 in vacuum. In vacuum, it is 0. And this is positive for paramagnetic and ferromagnetic materials. So in the next lecture, I'll be discussing about different types of materials, magnetic materials. There we will discuss more about this value of chi being positive. But you have to remember that whenever we are considering paramagnetic and ferromagnetic materials, chi is positive. And for diamagnetic materials, which cannot be magnetized easily, the value is negative. Chi is negative and it has no units. Now, if you are considering this equation, M is equal to chi into H, and chi is equal to what? Mu r minus 1, or mu r is equal to chi plus 1. Anyway, we write. So we can write M by H is equal to mu r minus 1 and chi is equal to M by H. So how we are just trying to understand how to express it in different forms. How do we write the value for mu r in different forms? So M by H is equal to mu r minus 1. So this simply implies mu r is equal to M by H plus 1. Or M by H is nothing but chi. So this will be chi plus 1. So when mu r is equal to chi plus 1, so chi will be equal to mu r minus 1. So to get one value from the other, we have chi is equal to mu r minus 1 or mu r is equal to chi plus 1. And we have already seen chi is equal to M by H. So mu r is equal to 1 plus chi. Now coming to the magnetic moment due to electrons. So whenever we are talking about magnetic moment, this magnetic moment can be due to electron or due to the spinning of electron and also due to the particles that are there in the nuclei. So the motion of the electron is considered as closed electric current loop, which produces a magnetic moment. So now you see here, we are considering an electron E, which is moving like this. This is the orbit, electron orbit, which is moving like this. So when the electron is moving like this, what happens? It is equivalent to a closed current loop, because whenever we have the flow of movement of electron, it gives rise to current. So this is a current loop, and this gives rise to magnetic moment. So we are writing this is the like North Pole and the South Pole, how they are induced when it is moving in this direction. So when the direction changes, the direction of the magnetic moment also changes. And the magnetic moment mu m is current multiplied by the area of the circulating orbit, the orbit in which it is circulating. That area, if you consider, you can calculate the magnetic moment. I is the current here, and pi r square is the area of the circular orbit in which the electron is revolving. So mu m is equal to I into pi r square. So the units will be what? Ampere meter square. Current is measured in ampere and the square of the radius is expressed in meter square. So the SI unit for magnetic moment is ampere meter square. Now when the magnetic dipoles that is atoms consisting of charged particles like protons and neutrons, which are there inside the nucleus. They also undergo orbital motion or spin motion. They too produce magnetic moment. Not only the electrons, which are orbiting around the nucleus, but the contribution due to the protons and neutrons, which undergo orbital motion. So, how we are considering it is, because the motion of any charged particle you take is considered as a closed current loop, and these closed current loops are giving rise to magnetic moment. Now let us see the origin of magnetic moment in magnetic materials. Why they are behaving so? So how they are getting the magnetic moment? It is a very important concept to understand. So where from this magnetic moment originates in a magnetic material? So it arises due to, number one, orbital motion of electrons, and its magnetic moment is called orbital magnetic moment of electrons, which is denoted by mu L. What mu L represents? Mu L represents the magnetic moment or orbital magnetic moment of the electrons. Then it is also arising due to the spin of the electrons. So the magnetic moment due to the spin, we call it as spin magnetic moment, and is denoted by mu S. Mu S here represents the magnetic moment due to the spin of the electron. And then the spin of the nucleus, that is the protons, they majorly contribute to this magnetic moment. So this is called the magnetic moment or the spin magnetic moment of the nucleus, mu N or mu P. So we are having three things: mu L, this is due to the orbital motion of the electron; then mu S due to the spin of the electron; and mu N or mu P, that is due to the nucleus, orbital motion of the, spin motion of the nucleus. Now let us derive the expression for each magnetic moment. So first we will see the magnetic moment due to orbital motion of the electron. So we are going to derive the expression for mu L first. Mu L here is representing the orbital magnetic moment due to electron. Now we are considering an electron here, an electron which is having an orbital motion like this. This is the orbital motion with a velocity v. V represents the velocity here. This is the radius of the orbit if you are considering this is the origin or the center of the nucleus. So when this is moving, we call it as the electron orbit. It is nothing but the orbit in which the electron is moving. So we have considered an electron E, which is moving in a given orbit of radius r with a velocity v. And here omega is the angular velocity. Now, because of this, what happens? Whenever the electron is moving like this, it gives rise to closed current loops. So we are considering an electron of charge E, which is revolving around the nucleus in a time period t. What is time period here? It is the time taken by the electron to complete one rotation or to move along one fixed orbit. So we call it as the time period, and the radius of the orbit is r. So E is the charge, t is the time period, and r is the radius. Now the magnitude of the circular current, we have to find the current. So the basic formula for current I is charge upon time. So charge is represented by E and the time is given by t. Capital T is the time period. So I is equal to E by t, and the time period t is equal to 2 pi by omega. So we know that omega is equal to theta upon t. Theta here, if it is making one complete rotation, it will move through an angle of 360, that is 2 pi. And the time it takes for one complete rotation, we are calling it as time period t. So T, capital T will be equal to what? 2 pi by omega. So we have taken T is equal to 2 pi by omega. And here omega is the angular velocity of the electron. That is why we are writing angular velocity as angular displacement upon time. So now I want to find I. So I is equal to what? E by T. I is equal to E by T. And now T is what? 2 pi by omega. For T I am substituting 2 pi by omega. So what we get when we take omega to the numerator, we have I is equal to E omega upon 2 pi. Now the magnetic moment of an electron is given by mu L, that is I into A. I into A, we will denote this by equation 2. Now mu L is equal to what? I into A. Let us substitute for I. We have found out I to be equal to E omega by 2 pi. And the area of this orbit we have considered, in which the electron is revolving, is pi r square. So when we simplify to pi and pi will get cancelled. So we have E omega r square by 2. So mu L, it is the magnetic moment of the electron, is given by E omega r square by 2. Now when you consider the angular momentum of any particle, we take it as mvr or mr omega square. This is equation 4. This is the angular momentum. Now we are going to substitute this equation 4 in equation 3. So what we have in equation 3 here? Mu L is equal to E omega r square by 2. So here we will substitute for omega r square, we will substitute L by M. Omega r square here is equal to L by M. So what we are writing, E mu L is equal to E omega r square by 2 we had. So for omega r square, we are substituting L by M. So we have EL by 2M. And we also have a negative sign which indicates mu L and L are in opposite direction. This is the angular momentum and this is the magnetic momentum. Because they are opposite in direction, we are writing mu L is equal to minus E by 2M into L. So this is equation 5. Now, from the Bohr's atomic model, what was the conclusion we had? The angular momentum is always an integral multiple of h by 2 pi or h cross we say. So mvr, angular momentum, is an integral multiple of h cross, or h cross is nothing but h by 2 pi. So what is mvr? It is nothing but L. So L is equal to nh by 2 pi, and here we are considering it as L. H is equal to LH by 2 pi, where L is the orbital quantum number which can takes on the values from 0, 1, 2, so on up to n minus 1, and capital L is the orbital angular momentum. Now we can write mu L to be equal to minus E by 2m. In place of L we are writing L into h by 2 pi. H here is the Planck's constant. H is the Planck's constant. So when we substitute this and simplify, what do we get? E h by 2 into 2, 4 pi m into L. This negative sign is there which shows that L and mu L are opposite in direction. Now this value EH by 4 pi m is a constant. E is the charge of the electron, which is a constant. H is a Planck's constant. 4 pi me, we are talking about the electron. So we consider the mass of the electron, which is again a constant. So E, H, 4 pi m, all are constants, and we write it as mu B. Mu B is called Bohr's magneton. Mu B is Bohr magneton, and since all the values are constant, we can find out the value and it comes out to be 9.27 into 10 power minus 24. So the value of Bohr magneton is 9.27 into 10 power minus 24. ampere meter square. So whenever we are calculating mu L, we need not do all this. We can simply write the Bohr magneton into L. And the value of L varies, depending upon the orbit. So it becomes easy when you remember the value of Bohr magneton. So what we have here is mu L is equal to L into mu B, where mu B is the Bohr magneton, which is a constant. Now coming to the spin magnetic moment. What is the spin magnetic moment? Like we see that the earth is revolving around the sun, and also it rotates about its own axis. The same way, whenever we are talking about an electron which is revolving around the nucleus, it also rotates about its own axis, which we call it as spin. So according to quantum theory, electrons should have intrinsic angular momentum due to the spin, because they are rotating about their own axis, which is, we are calling it as spin. And spin is also quantized both in magnitude and direction, and it will have only one value, either plus half or minus half. So the spin can have either plus half depending on the direction or minus half. So the magnetic moment that is produced due to the spin of the electrons, we are calling it as spin magnetic moment, and it is denoted by mu s. So mu s denotes the spin magnetic moment of the electron, and mu s is given by minus 2 into E by 2m into s. So this is the formula for the spin magnetic moment, minus 2 E by 2m into s. So what is s here? Spin angular momentum, like we have seen capital L as the orbital angular momentum. S will be the spin angular momentum. E is the charge of the electron and m is the mass of the electron. So we can write it as S is equal to SH by 2 pi. We can also use this SH by 2 pi. So now let us substitute for S, because we have seen mu s is equal to minus 2 into E by 2m into s, and for s we are going to substitute SH by 2 pi. H again is the Planck's constant. So when you substitute SH by 2 pi, what we have here is S can take the value of plus half or minus half. So I'll simply write 2 and 2 will get cancelled. We'll have minus EH by 2 pi m into S. So when the value of S is plus half, we get it to be minus EH by 4 pi m. And when the value of S is minus half, we get EH by plus EH by 4 pi m. So we are getting mu H is equal to plus or minus EH by 4 pi m, depending upon the value of S. So mu S can be written as EH by 4 pi m or minus EH by 4 pi. We have already seen that EH by 4 pi m is a constant, which we have called it as the Bohr magneton mu B. What is mu B here? Mu B is the Bohr magneton, and its value is constant. So we can write mu S will be plus mu B or minus mu B. So the spin magnetic moment is equal to the Bohr magneton, and there are two possible orientations, plus and minus. So in paramagnetic and ferromagnetic materials is due to the spin magnetic moment, and the diamagnetism is due to orbital magnetic moment. So we have discussed about two things now. Due to the orbital motion of the electron, which gives rise to orbital magnetic moment, and the spin motion of the electron, which gives rise to spin magnetic moment. So what we are concluding here in the classification also we'll be discussing again, that the paramagnetism or the ferromagnetism is due to the spin magnetic moment, whereas the diamagnetism is due to the orbital magnetic moment. Now coming to the last one, that is the nuclear spin. the magnetic moment of the nucleus is given by mu n is equal to EH by 4 pi mp. Mu n is equal to EH, like we have found for mu s and mu l. We can derive for mu n also. Mu n, we are talking about the magnetic moment of the nucleus. So mu n is equal to EH by 4 pi mp. E is a constant charge of the electron, H is constant, Planck's constant, and 4 pi is anyhow a constant. mp here represents the mass of the proton. We said the nucleus, whatever the spin we are considering, is mostly due to the proton. So we are talking as the mass of the proton. So this constant EH by 4 pi mp is called nuclear magneton. For electron, we have considered it as Bohr magneton, and this is due to the nucleus. We are calling it as nuclear magneton, and this value is also constant, 5 into 10 power minus 27. This value is 5 into 10 power minus 27 ampere meter square. So this value, if you see this nuclear magneton, the value is much smaller when compared to the Bohr magneton. So Bohr magneton is higher than the nuclear. So the contribution due to the Bohr magneton or due to the electron orbital motion is more when compared to the nuclear motion. So for reference, clarification for any point regarding this topic, you can refer to Introduction to Electrodynamics by David J. Griffiths, or you can also refer to Concepts of Physics by H.C. Verma, and you can also refer to Unified Physics, Electricity, Magnetism and Electronics by Dr. S.L. Gupta. So, thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.